Hello everyone, these are the STM analog question. There are four questions. Actually, there are more questions in the OA, but these are the relevant question. So, uh, there are the four questions. First this one. This is non-ideal op amp. Second is this one. Third and fourth. So first solve by yourself, then come back to the solution. Actually, there are six relevant questions. The two questions are from this a same circuit diagram, but in the second question, this op amp is non-ideal, and the second question is a derivative of this question. Now let's solve the question. So in first question, we can see there is an op amp which is an ideal op amp. Uh, Let me change my pen. Okay, this uh, okay. This is an ideal op amp. Wait a minute. Sorry, I will choose this one. So uh, this is an ideal op amp. Sorry, non-ideal one. Uh, its open loop gain is this, and there is an positive 5 volt to negative 5 volt supply, and this is V input. Okay, it's not supply, it's a biasing voltage, and V input is step input, and we have to find out V out. So let's solve this question. First, we can see the op amp is non-ideal, so no virtual short, no virtual ground. In this case, we have to solve by always finding current in this branch and this branch, and second by equating. Uh, Always remember there is one formula valid on the op amp if it's in virtual ground or not a virtual ground, or ideal or non-ideal. This formula is always valid for the op amp. What is this? Like V out is equals to gain of the op amp minus V positive supply minus V negative supply. So we have this formula, and we can equate the current. Like if I denote this current I, I can take this current I as well. Now, then I will make an equations. First equation is V in by R. This resistor is R, and this resistor is also R. So I will make a V in minus. I will. This is V negative on R. This current is equals to this current V negative minus V out upon R. If we solve this, we get V negative as V in plus V out by 2. This is the V negative terminal voltage. So V in by R, and then this minus V negative by R goes to this side, and this V out by R come to this side. So it will become 2V negative by R. So R to R cancel, and 2 come down. So we will come to this expression. Now for the second equation we use this one, like this V naught is equals to AS gain upon V positive is 0, and this is V negative, and we put this V negative in this equation, and we will get V out is equals to AS 0 minus V negative is this, like V in plus V out by 2 ka whole square. If we solve this, we come to the expression. We come to the expression. Wait a minute. V naught A S minus V in by 2. V in by 2 is there, plus V naught. I write V naught this side, at this side, and then this minus v naught by 2 come to this side, which will become the positive, and as v naught by 2, as v naught by 2, and then if we solve this, then we get the expression s v naught s by v in s, which is the transfer function of the circuit, is equals to minus as plus sorry, not plus, minus as upon as plus 2. This is the expression we get after solving this equation, as upon as plus 2. Okay, so put the value of as, we get as a dc upon 1 plus s omega p upon a dc 1 plus s omega p plus 2. Simplifying this expression, we come to this. I'm denoting this as transfer function. We come to this solution, minus a dc omega p minus a dc omega p. Sorry, not the minus a dc upon a dc plus 2 into 1 upon 1 plus 2 upon a dc plus 2 omega p into s. Now by this transfer function we can say this is a DC gain of the circuit H0. This is the DC gain of the circuit. This is tau, or we can say 1 upon omega pole frequency for the overall circuit. We can denote it as omega p dash. So this is omega p dash. We have to find out the output waveform, which is V naught. Output waveform which is V naught, and for this circuit ADC, for the DC gain, we can see the ADC is plus 2. ADC is very large quantity, and this is also large quantity. It's around 100 to thousands of value, same, and denominator is also 100 to 1000, but additional means 100 to 1000 two value. So these two values are almost same. So we can say that DC gain of the circuit is unity, and we can denote it as tau. Tau is a time constant of the circuit. So we can rewrite this transfer function as transfer function equals to minus 1 into, this is the DC gain of the circuit, 1 upon 1 plus tau s. We simplified this equation. So now we can write this V out. Equation is V naught s minus 1 upon 1 plus tau s into V in s, and we can see that our input is V input, which is unit step input, and we can represent unit step input in Laplace domain is Laplace transform is 1 upon s. So we can write this minus 1 upon 1 plus tau s into 1 by s, and when we come to time domain from Laplace domain, that v naught t becomes like that v naught t become like this, minus 1 minus e minus t by tau u t. Okay, so this is our final equation for v out. If we put the value of at t is equals to 0, we can see at t is equals to 0, this will become 1, and v out goes to 0 volt, and at is equals to infinite v out t, this will become 0. So overall v out become 1 volt. So we can see that at t is equal to 0, v out goes to 0, and at t is equals to infinite, v out goes to -1. So if we plot the output waveform with respect to the input waveform, sorry, mm, this is x-axis, there is time and there is v out t, and for the v input is a step input. This is vt 1 volt, which is a step input, and on with the and response of this input is at t is equal to 0 second, 0 voltage we have, but at t is equal to minus infinite, at t is equal to infinite, we have -1 volt. So minus infinite, it is a -1 volt, and there is a decaying waveform because the equation is an exponential equation. That's why it follows decaying path like exponential path. Okay, so it will reach to -1 volt. So this is our first question, sorry. So in the next question, in next question, they tell that this op amp is not this op amp is ideal. In the next question, the op amp is ideal. Like next question, this is resistor and what I'm mixing nothing. Positive rails or negative rail, positive 5 volt minus negative 5 volt, everything is same, but the condition is now the op amp is ideal and input is same and output is same. So and then they ask pro v out. So now we can see the op amp is ideal, and op amp is ideal, and it connected in negative feedback configuration, then we can confidently say that the op amp in op amp in virtual ground condition. Op-amp in virtual, we can use op-amp in a virtual ground condition. Virtual ground condition is valid in this case. So for the virtual ground, we can see the input is 0, so it will act as an inverting amplifier. For inverting amplifier, the transfer function is this is R2, this is R1. Transfer function is minus R2 by R1. This is the transfer function for our inverting amplifier. So V out by V in is minus R2 by R1, which is 1. So V out will follow the V in but in negative direction. So V out will always equal to V in, but the sign is opposite. So the output waveform will look like this. It is negative step. It is negative step voltage. This is output, and the input is, and this is the input. Okay. So this was our second question. Let's go to the next question. So in this question, we have to find out the range of V naught. We have to find out the range. So we can see it's a current mirror. It's a current mirror means this current will copy to this branch, exactly copy to this branch, as M1 and M2 are same. So and M1 and M2 are same, and they both drains of M1 and M2 are connected to the ground. So we can say it is a current mirror. So this 100 microampere will flow to this branch also, but we have to consider that that condition is for the current mirror, both MOSFET has to be in saturation. So our first condition is we assume that M1, M2 are in saturation. M1 and M2 are in saturation. M1 and M2 are in saturation. So if this 100 microampere flow in this branch, then 100 microampere will also flow in this branch. So if we check the voltage drop across this resistor R, so voltage drop across resistor R is 100 kilo ohm multiplied by 100 microampere, sorry. Then we see 100 microampere, and we see that then it's 10 raised to the power 5 multiplied by 10 raised to the power 2 into 10 raised to the power minus 6. We get 10 volt. So we can see that if we consider the current mirror, and we assume that this 100 microampere flow in this branch, then we see there is a 10 voltage drop of 10 ampere across this resistor. But it can't be possible because we have 2 volt supply and we are getting 10 volt voltage drop. It can't be possible due to energy conservation. 10 volt will not 10 volt will never appear if we assume this is a current mirror. So the practical scenario is, the M2 is not in the saturation. The M2 will not in the saturation region. M2 will not in the saturation. M2 will not come to in the M2 will not in M2 will M2 is not in the saturation region, but M1 always be in saturation region. M1 always be in saturation region. Why M1 is saturation region? We can see that our drain and gate are connected to the same potential. So this MOSFET is always in the saturation region. Okay. So now we find out that M2 is not in saturation, but M2 will always be on. M2 will always be on. And first, for the M1 condition, for the M1 MOSFET, we will assume this voltage is Vx for the M1, that M1 in saturation, so it will also in the on condition. And for the on condition of MOSFET, what the on condition of MOSFET is VGS always be greater than VTH. Okay, and the VTH is given as 0.5x, and our VG is Vx, that Vx is greater than 0.5 volt. Okay, okay, wait a minute. So for the next MOSFET, M2, for the next MOSFET M2 is not in the saturation region, means it is in triode region. For the triode region, the VDS is always less than VGS minus VTH, and and the on condition of the MOSFET is VGS is greater than VTH. This part is for M2 MOSFET. So VD is V naught, Vs is 0, less than Vg. Vg is Vx. Vg is Vx, and I forgot to mention one part in the question. In the question, they mentioned the Vx is 1 volt. In the question, they mentioned that Vx is 1 volt. Yeah, so I forgot about this condition. I also write it there. So that Vx is 1 volt. So Vg is 1 volt minus Vs is 0 volt minus Vth. We can see that V naught is equals to less than 1 minus 0.5 volt. So V naught is less than 0.5 volt. This is the upper bound condition, the V naught. And for the VGS part, for the on part, VG is Vx minus For the on part, no, so not the on part. um, on part we can say that Vx, which is 1 volt, which is 1 volt, it is greater than, it is greater, it is greater than 0.5 volt. We can't find anything about, we can't find anything from this equation, but remember there is one more condition, which is the, so we can't achieve anything from this equation. We only verify but that we uh, gate voltage is greater than 0.5 volt. Remember there is one equation which are for the current equation, that is sorry, that is VDS. VDS is greater than 0. Whenever VDS is greater than 0, then only the current will flow. So it is in it, and that in the circuit VD, this M2 is in triode region. There is some current is flowing. The current will only flow when this condition is satisfied, that VDS is greater than 0. If this is equal to 0 or less than 0, then current will not flow in the NMOS. So we have to consider we have to consider this equation also for the current following part. For the current falling point, that VDS is always greater than 0, then only the current will flow in the MOSFET. Okay, so that VD is V naught, and VS is 0, which is greater than 0. So this is the upper bound condition, this is the lower bound condition. Combining these two equations, we get V naught, which is less than 0.5 volt and greater than 0 volt. So this is our final solution for this question. And the secondary part of this question is, the second question they ask which MOSFET is in saturation and which MOSFET is not in saturation. So I hope you will understand which MOSFET is in saturation, which is not in saturation. So solution for this question is, M1 is always in saturation. I explained about this earlier. And M2 is in triode region or linear region, we can say. Okay, so move to the third question. In third question, they ask us to find the current I equation in the inductor. First, the t less than 0 part. In t less than 0, the switch is connected to the A point, which is to 10 volt, and at t is equal to 0, switch is suddenly move from A to B position, and we have to find the current. So first we can find we will find initial condition. Initially, initially when t less than 0, initially when t less than 0, the circuit in steady state, in steady state, and in steady state, the inductor will short, because because current is constant, and for the constant current, inductor will short. So circuit will look like this. This is 5 ohm resistor, this is inductor which is short, and this is 10 volt. And we can see the initial current flowing. The initial current flowing is 10 volt upon 5 ohm. This is 5 ohm, and this is 10 volt, which is 2 ampere. So initial current, we find out that initial current is 2 ampere. Now our our secondary condition is, when at t is equal to 0, position switch position change from A to B. So circuit become like this, and now it is connected to 15 volt, and this is 5 ohm resistor, and this is R and L. Now it will become simple RL circuit, where we have to find out the current. And for this type of circuit, the current equation is I final, which is I infinite, plus I initial, which is I 0 minus, we can say, minus I infinite, which is I final, equals to E minus t tau. And time constant for this circuit is L by R. L is 5 Henry, and R is 5 ohm. So we can see the time constant for this circuit is 1 second. And I final, we can find out the I final as well. As I final means at steady state for the circuit. When will we achieve the steady state for the circuit? When this inductor becomes short, means the current flowing the current become constant. Its constant current will flow to this circuit. So then this circuit come to the steady state. So for the constant current inductor will short. This is the steady state condition. The circuit behave like this. Only 15 volt with 5 ohm resistor, and the current. This is the final current, which is T infinite current, which is 15 volt upon 5 ohm. 3 ohm current. Sorry, 3 ohm, not 3 ohm, 3 ampere current. Okay, so we find out that I infinite is 3 ampere, and we can put this current in this equation, which is 3 ampere plus and I0 is we find that I0 is 2 ampere. This is I0 current, I0 minus current, and as this is the initial current, so this is the initial current, which is 2 ampere minus final current is 3 ampere. E minus t, tau. So I is 3 plus 3 plus not plus 3 minus e minus t. This is the final current equation. And for now we will move to the next part. This is the tricky question. So we have to find out V naught. What is the V naught? Let me redraw the circuit, and by this we can say this is PMOS and this one is NMOS. So the circuit is the combination of NMOS and PMOS. Okay, uh, this is V naught, this is VDD, and its gate terminal is connected by the source of this NMOS. This is VDD, this, this is VDD, this is VX. Okay, we can see the NMOS. NMOS always in saturation region, and V. There is one more condition in the question is whether VTH NMOS is greater than VTH of PMOS. This is another condition for this question. And by the drain of the NMOS and the gate of the NMOS are sorted, so we can say this, and this is in saturation region. In saturation, this MOSFET in saturation region. This MOSFET in saturation region, and the condition for the saturation region of NMOS is the saturation region is VDS is greater than VGS minus VTH. And okay, so the VD is VDD and VS is VX, which is uh, okay, VDS, VD is VDD, and the VG is VDD minus Vx. Oh, sorry. Mm, there is one more condition, which is the on condition for the MOSFET. Uh, the VGS always greater than VTH. This is the on condition for the MOSFET, and the VG is VDD minus Vx and VTH. So we can find out the Vx, which is always less than VDD minus Vx. So the minimum value of Vx is minimum value. sorry, not minimum, sorry, maximum value or minimum value, we can say uh, maximum value of Vx, which is uh, which is well, not maximum value, sorry, minimum value of Vx is Vdd minus Vx. And for the as for the second PMOS, the on condition for the PMOS is on condition for the PMOS on condition for the PMOS is VSG will greater than VTH VTH P modulus of VTH P. That there is one more thing, that threshold voltage for the PMOS always be negative, and the threshold voltage of PMOS always is negative, and always is small compared to always small and negative compared to threshold voltage of NMOS. मीन्स ये वाला जो थ्रेशोल्ड वोल्टेज होता है पीएमओस का, वो बहुत ज़्यादा कम होता है threshold voltage of NMOS के. So the voltage drop across between drain to source primary is also less, and we can say that the NMOS, sorry, PMOS is the good candidate for the passing of high voltage. Okay, so मीन्स हम कह सकते हैं कि जो PMOS है वो बेटर कैंडिडेट है हाई वोल्टेज पास करने का एज कंपेयर टू NMOS. So the on condition for VSG must be greater than VTHP. So we can found that Vs is V naught minus, no, sorry, not V naught, because this is drain and this is source. So Vs is VDD minus VG is Vx. I'm currently writing VSG. So VDD minus, now we can put the value of Vx, which is VDD. I am also including the sign minus plus Vx. VDD is sorry, not Vx. It is VTH N. So we can say that VSG is equals to VTHN, which is greater than VTHP. So MOSFET is on. If the MOSFET is on, it will always pass the high voltage. It will always pass the VDD. So all the that we prove that the VSG is on, and the VTHP is the small drop voltage. So all the VDD comes to V naught. So V naught final is VDD. Okay, I hope you like the